Hello, everyone. Going to go through some of the loop and function practice problems and take you through my thought process solving them and then a live coding of the solution. Definitely get through the my Euler, maybe get through the other ones as well. So if you're watching this, make sure you've tried the problems first. It'll be a lot more beneficial to have struggled with them for a little bit and then watch the video than it will be to go straight into the video and think, okay, I could do that. Remember, desirable difficulty, right? So the more you struggle with something, the better you're going to learn it. Move out of the sun. All right, so this first problem, write a function called my Euler to approximate Euler's number by summing the first m terms in the series. So we go from n equals 0 to m of 1 over n factorial. Okay, so first we have to reference back to the problem solving steps. All right, number one, read the problem. So we know we just need to sum that series to a given point. So that's understandable. Thinking of the tricky cases, well, I don't think there are any tricky cases for this problem because maybe 0. But the first 0 terms would just be 1 over 0 factorial. So that's a possible tricky case. We'll write that in our function docstring. Then solving a small example by hand, and writing tests for the tricky cases, and then writing pseudocode. So a small example by hand. Let's go over to a whiteboard. So we've got sum from n equals 0, wow, that's awful, to m of 1 over n factorial. Hopefully you all can read that. So if we wanted to try to m equals 2, for example, we would sum 1 over 0 factorial, 1 over 1 factorial, and that would be it. So 1 over 1 factorial, that's 1, 0 factorial, 0. Or maybe even undefined. So then we get our approximation is equal to 1. Not a very good approximation. For E, we're looking for something around 2.7. So let's try approximation of 3. Well, don't need to write those out again because yeah, we already have them there, but adding the next term, 1 over 2 factorial. 2 factorial is 2, so plus 1/2. So we get 1.5 for this. Let's write the rest of it in. So 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial, and it looks like we're approaching that 2.7. So we're convinced that the problem statement works. We have a thorough understanding of the problem. Now I can get rid of this whiteboard and we'll go over to our Spider IDE. So we're going to start with our function definition, and we're just going to write out those tricky cases. So we're going to take in m, which is an int, and we're going to return a float, our approximation. Start with the doc string as always. So my Euler, skip that, approximates Euler's number by summing the first m terms. M is how many terms to sum. And it returns float. It's an approximation of E. And then we'll add in our examples section. Examples. So we've got that one tricky case. We know we want my Euler of 0 to return 0. Oh, and thinking of testing something like this, where we're testing an approximation, when we test it, we're going to have our epsilon. So we can use these docstring tests by doing something like my Euler 0 minus, or we want my Euler 0 to return 0. It's a bad approximation, so I'd say we don't use this as our test case. But we want my Euler of, let's say, 100. This should be pretty close. So this minus the actual math.e, actual Euler's number. We want this to be, this whole thing, to be less than, let's say, 0.0001. No, we don't know if this is going to be positive or negative. So we want the absolute value of our approximation minus the real number to be less than some delta, in this case 0.001. And we want that to be true, this whole statement, so we'll say true. Another good test case, let's just copy this down. We can say even at 10, it should be reasonably precise. Let's see if we can hit that precision. I'm not sure if we will, but we can adjust that later. Now our next step is going to be writing pseudocode. So Python-esque list of instructions. Since I can't really write them out in the whiteboard, I'll just write them out and then we'll translate it into Python. So writing it out here, we know that we have to compute the sum of 1 over n factorial. So this is our goal. So sum 1 over n factorial to the first n terms. I like that better. Sum the first m terms of 1 over n factorial. So we know that we need to loop m times, and then inside that loop, we're going to add 1 over n factorial to the sum, which means we need to keep track of a sum out here. Let's start that at 0. Since there's no reason to start it anywhere else, sums start at 0. So we're going to loop m times, add 1 over n factorial to the sum starts at 0, and then eventually we're going to return sum. And so this is already pretty close to Python, right? It's not far off. So now we'll convert that to actual Python code up here. Let me just make this a comment. And we'll add a comment here saying this is our pseudocode. Great. So we want to actually convert that into Python. Well, sum equals 0. That's already Python. And then we can do this with the while loop, but by now everyone should be comfortable with for loops or have at least watched that lecture. So we'll do this one with a for loop at first. So we're going to go for n in range m. We need to add 1 over n factorial to the sum. So we do sum plus equals 1 over math.factorial. Now to use the math package, we have to import and then eventually our return sum that is already Python. So pseudocode and Python are very close together a lot of the time. Now we've got our function written, so we need to test it. So we make our if name equals name, import doctest and doctest.test. So this should run our tests here, and hopefully we see no output. All right, no output, that's fantastic. Just to get a visual look at what's going on inside of our if name equals main block, we can print my Euler of, let's say, 10. Let's just see how close we're getting. We run it and we see, okay, that, if I just saw this, I'd say that looks like Euler's number because I only know the 2.718. So I'd say that's good enough. It looks like we're within this epsilon. Now, another way to write the tests is with assert statements. That's the way that we are familiar with. So we could just copy this identical test and then assert. No, didn't copy. Assert that this is true. I'm not sure what that was. Now, if we wanted to assert that the difference was greater than this epsilon for some reason, we'll see an error thrown, an assertion error. But the takeaway from this is that asserting, you can make an assert statement in your doc test by adding this true here. And this is exactly equivalent to this. Right, so that's the Euler's number one. See how much battery I've got left. 2%. So that's going to be it for these demos, and I'll upload a video of more later.